The final class of vulnerabilities discussed in the lecture on application security is type confusion, which is an attack that is specific to C++. So, let's give some information for those who are not familiar with objects in C++. So C++ allows you to write classes, which, when you come from C, you could see essentially as structs that are there to tie data to functions. So the data is stored as it would be in a struct, but now we can also associate functions with those data. Now, an instance of a class is known as an object. And it's important to know that in C++, unlike many other object-oriented languages, objects can be both on the stack and on the heap. Well, objects, as is usually the case, can have a constructor and a destructor, where the constructor initializes the fields of the object and the destructor basically handles anything that must be cleaned up there. So for example, freeing any memory that might be allocated in the constructor. And what is nice about C++ objects is that these are automatically called. So if we have a stack object, it calls the constructor whenever the function starts, and it calls the destructor whenever it returns, even in exceptional cases, such as when an early return or an exception is raised. Now, this can help a lot in ensuring that destructors are consistently called at the right time. And of course, constructors help prevent uninitialized variables, because in C, everything on the stack was uninitialized, essentially. Whereas now, if we have an object on the stack that has a constructor, at least we can be sure that the constructor will be called to initialize the fields of the object. In case of a heap object, then we have to use the new and delete operators, which not only allocate the right amount of memory, but also call the destructor and the constructor when needed. So again, this helps us make sure that we avoid other memory vulnerabilities. However, as we will see in this lecture, there are also vulnerabilities that are specific to C++ objects. So, why would we use C++ objects? Well, first of all, they're important for code organization. So if you have a very complex program, think about the browser or a compiler, then you can use them to organize your code in a neat way, indicating clearly which code belongs to which data, and also still allowing you to be fast. So this allows you to avoid other object-oriented languages, like say Java, which are slower than C and C++. Moreover, automatic destructor invocation makes memory management easier. So it allows you to make sure that regardless of what happens, whether it is an exception or a return or whatever, whenever a function returns, eventually the memory will be freed. Or other deallocation operations such as closing a network connection, closing a file or a database, or so on. That any of these will happen automatically. This is another important benefit of C++ objects. Moreover, polymorphism and templates allow for code reuse. We will not discuss these concepts here, but if you delve into C++ objects, you will see that there are many of these features which allow you to use the same code for multiple purposes. Since less code means fewer bugs and easier debugging, this is also great for security in general. Then finally, they also allow so-called smart pointers. So in C, we had to do all the memory management ourselves. In C++, we have the ability to use objects that are called smart pointers, where the constructors, the destructors, and also the overloaded operators perform special operations to make sure that memory is allocated and deallocated exactly when needed. Now, this avoids use after free vulnerabilities and also memory leaks, at least when used correctly. As such, using C++ objects can have many security benefits. But as we'll see, there are also some drawbacks. First, of course, we still need to be very careful. It's only safer than C when handled properly. For example, initialization is often taken care of now by the constructor, which in some cases will prevent uninitialized variable vulnerabilities. However, this means that we do need to do this explicitly. And this will not happen for primitive types. So if we have these primitive types, it's much easier to overlook their initialization, because some of the other stuff, like say strings, does not need to be initialized explicitly. So even though some of the memory management is automatic, other parts are still manual, which can be very confusing. Moreover, C++ is one of the few languages that allows full multiple inheritance. So you can have an object deriving from multiple parent objects, which gets very confusing if you have diamond-shaped inheritance. So if basically an object descends from the same ancestor in multiple ways. What you can do pretty much in C++ is class inbreeding, which is not a good thing. I already mentioned this briefly, but C++ allows inheritance of classes. Now this means that one class can derive from one or more other classes, where deriving means that the class that derives from the other class, so the child, contains all the data stored in the parent class or classes. It also means that all the functions that can be called on the parent class can equally be called on the child class. And in practice, it turns out programs often have very complex hierarchies of classes. So think, for example, of a document object model in a browser, which contains many classes that are interrelated. So this is very useful, but it can introduce a lot of complexity. It is also one of the features that really clearly distinguishes a simple struct in C from a class in C++. Now, what is special about this and important for this lecture is that an object pointer can be safely cast from a child class to a parent class. And this happens all the time. In fact, the compiler does this implicitly. So think about the case where we have a circle class that descends from shape. So we're saying every circle is a shape, but this does not mean every shape is necessarily a circle. So we can pass a pointer to a circle object to any function expecting a shape pointer, but not the other way around, because the shape might equally be a triangle or a square. And in this case, obviously, it would not be correct to cast it to a circle pointer. So casting a child type to a parent type is implicit. We don't need to think about it, the compiler does it for us in cases where it can be done. If we try to do other casts between objects implicitly, it will not work, and the compiler simply gives an error stating that the type is incorrect. Still, we may need to do this sometimes, although typically it is a bit of an indication of bad program design. But in some cases, we need to cast, such as life. So C++ actually offers multiple typecasts, and the problem of type confusion that we're discussing here could easily be solved by just using a different type of typecast. So, first type of typecast to consider is reinterpret cast. Now this is pretty similar to the C-style cast. It just makes sure that there are no checks. Instead, the compiler will simply use the data of one type as another type, effectively reinterpreting the meaning of the bits. This assumes that the programmer knows exactly what they're doing. So this relies on the representation being actually interchangeable between the two types in some meaningful way that the programmer understands. Of course, we all know that programmers make lots of mistakes, so this is inherently unsafe. So reinterpret cast is fortunately not used a lot. Instead, what we see is the static cast. What static cast does is a compile time check. So at runtime, it does not perform any checks, which means it's still as fast as reinterpret cast, because the check is not performed at runtime. However, it allows any cast that might be valid, so including any parent-to-child cast. Right, so we can easily cast, say, a square to a circle if it was stored as a shape pointer. Now this is still unsafe, and it's still a source of bugs. Finally, we have dynamic cast. So dynamic cast is actually safe. It performs a runtime check to make sure that we cannot cast one type of object to another type of object that is not its ancestor. Right? So we cannot cast objects to, say, a brother or sister object, a sibling object. So we have a runtime check, which is slow, which is also why dynamic cast is not widely used. Now, there is another more minor issue with dynamic cast. So sometimes people like to live on the edge and create objects that they know have the same layout, or at least sufficiently similar layouts, and cast between them even though they are not actually the correct type. Right? So in these cases also dynamic cast will fail. Now this is something they consider a false positive because they want to convert these objects knowing that in principle it should be safe. So again, this is a reason why programmers often use static cast in places where dynamic cast would have been safer. Now, what can go wrong if we use the wrong cast? We can get type confusion. So, static cast is common but unsafe. The vulnerability in the case of type confusion is that an object can be cast to a wrong type. This is often not very obvious from the code because objects tend to be passed around a lot. And we might simply work on an assumption that some pointer of a parent type is pointing to a particular child type. If this assumption is incorrect and an attacker is able to somehow manipulate the program into putting an object of a different type in that location, then this may be possible to be abused. So this bug is one for which there are many opportunities in complex object models. And there's also typically a very large attack surface. So if you're thinking about, for example, a browser that allows you to run JavaScript manipulating all the objects that relate to the document object model of the browser. In that case, JavaScript can do a great deal of confusing things to these pointers. And even though JavaScript cannot itself directly calls a typecast, it can force the browser to do so. Now, if the browser is not careful enough at that point, there could be type confusion. So, there's many opportunities for type confusion in some programs that are especially important to be protected. Moreover, these vulnerabilities are very predictable for attackers. So before we saw the stack vulnerabilities, which depend on the memory layout as determined by the compiler. We saw heap vulnerabilities that depend on the memory layout as set out by libc. However, in this case, the layout of objects in memory is completely dictated by the ABI. So the ABI set by the operating system decides what the object layout is. This means that type confusion vulnerabilities are very predictable and can even often be reused between different compilations of a program, different platforms, as long as they use the same ABI. Well, what happens if we perform the wrong cast? So static cast will simply perform its cast, creating a pointer of one type, pointing to an object of another type. Now, this means there is a mismatch between what I will call the runtime type and the compile time type. So the runtime type is the object that is actually stored in memory, whereas the compile type is the type of the pointer pointing to it. Now, if these two are incompatible, that is, if the runtime type is not either a descendant or the class itself of the runtime type, of the compile time type, in that case, we have an error in our state. We have a pointer pointing to something that's wrong. Afterwards, what will happen is anytime we read or write members according to this wrong type, we can basically break protections. So we could, for example, write an integer to a pointer variable, which often allows us to abuse the situation as an attacker. We could also go out of bounds of the object. So if the runtime type is a smaller type of object than the compile time type, we might be able to read or write out of bounds of the object as well. Here we have a very simple example of a type confusion. Now we define three classes. The shape is the parent class, and it's the parent of both the circle and the rectangle. Now both of these classes individually provide an area function, which computes the area of the object. They also provide a constructor, and the constructor simply initializes all the local variables to the values provided to the constructor. So in case of the circle, that would be a radius, which is initialized. In the case of the rectangle, it would be a length and a width, which are stored as fields in the object. So the fields part is basically equivalent to a struct, whereas the functions shown below are simply functions that operate on this struct by default. Now, both of them derive from the shape. Let's see what we can do with this code. So first we create a circle object by invoking its constructor. The radius parameter in this case is 42, so we're creating a circle object with a radius of 42. Now, we can use an implicit cast to make this pointer into a shape. So here there's no need to make clear what kind of cast we're doing. It's obvious to the compiler that this is legitimate. If the shape had any data stored, it would also be stored at the start of the circle. So any pointer to a circle object is also a valid pointer to a shape object. This is guaranteed because of the relationship between the two. Now, we are allowed to static cast the shape object to a rectangle object because, as far as the compiler is concerned, there might actually be a rectangle object in there, as the rectangle does derive from the shape. So this is exactly what we do here. We cast the circle object to a rectangle object. Now at this point we have a pointer to a circle object stored in memory, but the pointer is of a rectangle type. So if we call a function on this pointer, like in this case the area function, we call the rectangle area function rather than the circle area function. Now, what happens in memory, the first variable stored inside the object is actually at the same location. So the R and the L fields are in the same locations. Whenever we read or write the L field in the rectangle, we're actually referring to the R field if we have this type confusion vulnerability. However, the circle object only has one field, whereas the rectangle object has two. So the second field, W, is past the end of the circle object. Let's see what the impact of this is. So we compile the program. We don't have to have all the special switches this time. And then we run it. And we get this output, which is a huge number. So this is the area we computed for the rectangle object. Now on the right hand side, we see the function used to perform this computation. Let's take a good look what happens here. So first of all, we see that there is a parameter to the function, RDI. But we did not explicitly mention a parameter in the code. So what happens here is if we have a member function of an object, this member function will get a pointer to the object passed to it as an implicit parameter. And this parameter in this case is stored in RDI. So we're storing RDI here as a local variable, RBP -8. Then we see that we're loading a value from a location relative to this variable. So we're dereferencing RBP -8 here and putting it into REX. So REX at this point contains a pointer to the object. Then we dereference REX itself, which means we get the first field stored at the start of the object. This is what happens here. So we're trying to read the L field of the rectangle here, but instead we get the R field of the circle. Now the next one is where it goes wrong. So we read the W field of the rectangle, which is at REX +8, as we more or less expected. For the circle, this is out of bounds. So what do we read? It's just like before. We read whatever is next to it. Well, if we take the time to compute this number, what its meaning is, we find that we can divide it by 42. So of course the area of the rectangle is the length times the width. So we know the length, which is 42, because that is the radius we set in the circle object. But now apparently we have some number multiplied by 42, which is this. So it turns out, if you look at what we did here, that this is actually this value. And this value looks very much like a randomized pointer. So what do we have here? We have a leak of a pointer, as we will see in the defenses section. This is something that actually breaks the ASLR defense. So we have an actual exploitable type confusion bug here in this very simple program.